Hello, calculus class. We're going to look at vector functions, at least as they apply to your 12.2 assignment, which should probably be the second assignment that you're getting this year in Calculus 2 for vector functions. So let's look at a couple of the textbooks examples, and then I'll leave you to look at the other ones if necessary, or some of the other videos I've posted. Okay, so the one we went over in class this year was this one. It was evaluate to find a definite integral for a vector function. So for some one finite spot to another finite spot, if you integrate a vector function, what do you get? So let's have a look at that. So we've got a vector function, it's a three-dimensional vector function, and I think you really shouldn't find it surprising at all that to integrate a vector function, you just integrate each one of the components. That should make sense because remember the advantage of this I, K, J unit vector notation, instead of just, writing it like this, is if we tried to integrate this kind of a thing where we've got three components, you might not be sure how that integral dt works. That might be a little bit mysterious, but one of the advantages of the IJK thing is that you can just add these. I mean, really, you're just adding. This is a linear combination of terms, and we know that to integrate three terms, all we have to do is distribute that integral. We know that integrals distribute across summations or differences. So you can basically just integrate the first term dt, and then distribute that integral and integrate the second term dt, distribute that integral and integrate the third term dt, and you've got the integral of the entire vector function. Uh-oh, a cat is already interfering. Let me go and evict this feline. Okay, so let's go ahead and do those three integrations, and that's pretty much it. So not a very difficult problem, but one that I thought we should talk about. So let's see, that first integral, so if we integrate the vector function, what are we going to get? So I'm just going to say that this is equal to, or that this is equal to. Either way, it should be fine. So if we integrate the first term, what are we going to get? T to the 1/3 plus 1 is 4/3. Divide by 4/3, and that's the same as multiplying by 3/4. So we're going to have that guy. I'm going to leave I, J, and K for another notation. Another color. So I'll just do those in a separate color. We're going to integrate that from 0 to 1. Alright, so then we're going to have plus, what is the integral of 1 over t plus 1? I think the antiderivative of that should be the natural log of the absolute value of t plus 1. We're going to evaluate that from 0 to 1 with the fundamental theorem. Then we're going to integrate this guy, which is going to be plus, you know what? Not plus. Let's think ahead a little bit. It's going to be minus e to the negative t, right? From 0 to 1. And there we go. So we'll have that for the I component of our resulting vector, that for the j component of our resulting vector, and that for the k component of our resulting vector. And each one of these should be just a value. So remember, when we integrate from one finite spot to another finite spot, we should get one finite answer, but in this case we're in the three-dimensional vector system, so we should get one finite three-dimensional vector when we're done here. Okay, so let's see, that's going to be equal to 3/4. Then 1 to any power is 1, and 0 to any power is 0, so that's easy. So then we'll have plus the natural log of 2, I don't have to use absolute value anymore, minus the natural log of 1, which of course is going to go to 0. And then we're going to have minus, and then here we're going to have e to the negative 1, which is 1 over e, and then e to the 0 is of course 1. Okay, let me get my notation in there, I, j, and k. And we're pretty much done. We just need to simplify, and we've got our vector, our integrated vector function. So we get 3/4. In the I direction, I'm just going to give up on my color coding here. And we've got plus the natural log of 2. That's the number that describes our displacement in the y or j direction. And then we've got this number, which is not super nice. So you know what? I'm going to write it out first. Instead of saying minus, I think I'm just going to rearrange that and factor out a minus and go, that's 1 minus 1 over e, whatever that value is. If you want to make a common denominator, by all means do it. But there we go. So that's in the k direction, that's in the j direction, and that's in the I direction. So that's the vector, the three-dimensional vector that comes out from doing that, that integration from 0 to 1 of that vector function. Okay, There we go. So there's one vector integral problem. Let's look at this one. Here's another one. So it says find the antiderivative. Okay, so we're starting with r prime. We're starting with the derivative vector function in this case, also three-dimensional. And this is one that I think you'll run into more often than not in more advanced classes and on the AP exams. This is a really important one. So we've got an initial condition on this one. We say an initial position vector, and it's a finite vector of this. So why do you need that? Well, I think it should be pretty obvious once you try to find the original or antiderivative vector function. So of course, to get r from r prime, I integrate with respect to t. That's not crazy. We just learned that to do that, I'm going to go this dt, I'm going to go this dt, and I'm going to go this dt. Okay? So what are we going to get? We're going to get that r of t is equal to, and the integral of cosine of t, that should be positive sine of t, right? This wasn't just t though, it was 2t. So you could do the u substitution if you want, but I'm just going to undo the chain rule by dividing by 2. So if you're not sure about that, go ahead and do the u substitution. Alright, but I'm pretty sure. So then I'm going to say, okay, minus 2, I'll pull that 2 outside of the integral here. And the integral of sine is, of course, positive. No, it's negative cosine, so negative negative is going to make a positive. So then we've got cosine of t here. All right, and then I'm going to have plus, what is the integral of this guy up here? This guy up here, I think, is one that we should remember. That is the inverse or arctangent function. That's its antiderivative. It becomes the inverse tangent function. Okay, so, I almost committed one of the worst blunders in all of calculus here, right? When I look at integrating these three things, if we ever just integrate a function indefinitely without finite limits, right, like the previous problem, don't we have to add plus c? I think so. And these are three different integrals. So I think we're going to have to add three constants. So this is going to get one, this is going to get one, and this is going to get one. And they're not the same, so I'm going to subscript them differently. So this is plus c1, this is plus c2, and this guy is plus constant 3. Alright, well that's not very satisfying. I have three arbitrary, well not arbitrary, I shouldn't say arbitrary, I should say three finite constants, which I don't know. They're unknown constants. So how do you find them? How do you resolve them? Well, that's why they gave you this initial condition. It's not because this is like a differential equation or something like that. It's because that's going to help us nail down the finite values of each component in each vector direction, the I, j, and k direction, of course, or x, y, and z direction. That we need that vector function to accomplish. So that's what we're going to do. We're going to say, okay, so let's do them one piece at a time. So I'll give myself a little bit of space and say that the sine of 2t over 2 plus c1, that's supposed to come out to, what, 3? Yeah. So we're supposed to eventually, because of this initial condition, at 0 you're supposed to get 3 in the x component. So on our vector function that we've just created with integration, at 0 you're supposed to get 3 in your x component. Oh, at 0, I need to put 0 in then for t. This should have been 0 and not t. Okay? And of course, if I didn't put something in there, I would have an equation with two unknowns, which I can't solve. So what is the sine of 0? If we think over here at 0, isn't the sine of 0 the y-coordinate at 0, which is nothing. So that just says C1 equals 3. Good. There we go. And then this guy is going to be a separate equation. So we're going to have 2 cosine of t plus that second constant. That's supposed to be negative 2 when we plug in 0. Okay, that's what the condition told us. So right here I'm going to plug in 0. So 2 cosine of 0. Cosine is the x value at 0, which is 1. So that's 2 times 1 is 2, plus c2 equals negative 2. So that says c2 is negative 4, of course. Okay, got my second constant and my third constant. I'll just do over here. So that's going to be the inverse tangent of 0 plus C3 is supposed to be 1, right? Because of 1k in the initial condition. Inverse tangent of 0 is 0. I just always like to remember the inverse tangent function looks like this. So it goes through the origins. That's 0 plus C3 equals 1. So C3 equals 1. So my final answer should be that my vector function, I'm just going to do it down here in green, is the sine of 2t over 2 plus 3. Then I've got plus 2 cosine. Get some of this out of the way. There we go. So I've got plus 2 cosine of t minus 4. And then I've got plus the inverse tangent of t plus 1. And see, now I want to clean this all up. And remember, this is 3 components. This is a vector function, so that's in the I direction. That is in the j direction. And this is in the k direction. Okay, so there we go. We found another integral of a vector function. Let's look at one more problem involving those new products. So if you haven't watched them already, you need to make sure that you've watched the dot product introduction and cross product introduction. We'll work more with those when we come back from spring break and learn a little bit about their meaning, so you have a little bit of three-dimensional calculus as well. I don't think they're going to be on your AP exam, but we'll learn about them a little bit today. So you just were introduced, if you watched those videos or in class, if I described how to just do the algorithm for the dot product and the cross product. I had trouble doing that, so we're going to be doing a dot product right here and a cross product right there. Okay, so we've got two vector functions, and they want us to find the derivative of the dot product of those vector functions with respect to time, and the derivative of the cross product of u dot its derivative with respect to time. You can do these a couple different ways, so I thought we'd do them a couple different ways just to have a little bit of practice. So one way you could do them that would be probably easier is to just do the dot product first. You might not be sure that's the way this works, though, because you should be thinking about, if I have notation like this, it's probably a safer bet in case something is fishy, in case something doesn't work exactly like the way I expect it for a new notation type like this. Maybe I should take the derivative according to the product rule. So let me do way 1 with the product rule, because that's a really safe way to do this, even if you don't know much about the problem. So the first way to do this is to approach it with the product rule. So that's going to be equal to, that guy is going to be equal to what? If I use the product rule, then I'm going to have r of t dot, so because there's two kinds of vector multiplication, the dot product and the cross product, this one says use dot product, so I'm going to go r of t dot u prime of t. In other words, first times derivative of second. So then plus the second vector function dot the first vector function prime. So you can see that's just a plain old product rule. So let's see how that works. Well, I need u prime and r prime up here, so I'm going to get those guys. I'll just put them in green up here. So let's see what r prime is. I'll put it right above r. R prime of t should be, for this guy, what is it, negative 1 over t squared. And then that's in the I direction, and then minus, oh, that's just a constant, so that's going to go away, so nothing in the k direction. Let's put plus 0j. I should say j direction, and the derivative of natural log is 1 over t in the k direction. Okay, and then up here, I'm going to use, I'll just do u prime up higher. There we go, so u prime of t is going to be, what? It's going to be 2t in the I direction, minus 2 in the j direction, and that's just a constant, so there's nothing in the k direction. I'll hold the place value just in case we need it for a cross product or something in a moment. Okay, so we're going to do r dot u prime. So this dot u prime, remember you take each component, you multiply them together, and you get the scalar that comes out of that. So r dot u prime. What's that going to be? So pretty easy, right? You're going to have this times this, which is 2, and there's no t left, right? You're just going to have 1 over t times 2 over t is going to be 2. And remember, this is a dot product, so I'm not going to put I here. I just write the number that comes out. So I'm going to have 2. Okay, so that's the first contribution. Plus, then I'm going to do the y components multiplied. So negative 1 times negative 2 is what? 2? Okay, and then I'm going to add the contribution of the third components multiplied. So natural log of t times 0 is going to be what? 0? Yep. Okay, so I've done that one. Now I'm going to do this one. So now I've got u dot r prime. So I'm going to go this guy dot that guy. So t squared dot that is totally cancels out to -1. And then -2t times 0 is no contribution. And 1 times 1 over t is 1 over t. That's the k contribution. So in this dot product, since I didn't have actual numbers plugged in, since these were all variable expressions, notice the dot product can come out to another variable expression, but it's not a variable expression in a certain component. The dot product is a way to multiply vectors that produces a scalar. So you can see that this is a scalar. It's 4 minus 1, or 3 plus 1 over t. That is not a vector, it's a scalar function. Okay, it doesn't have an I, j, a k over here. So that's the way I wanted you to see that first. So now you could have approached this problem with a separate way. You could have been like kind of like PEMDAS reasoning, or go inside first and do r dot u. So what is r dot u? If you go 1 over t times t squared, let's do that first. So let's do r prime, or r dot u. So what is that going to be? That's going to be t plus, remember, no vector component, and then -1 times -2t is 2t, okay, plus no vector component. Natural log times 1 is natural log of t. So that's all one thing, and then we're going to take that whole thing, right, that whole thing, and we're going to take its derivative with respect to time. So d dt operated on both sides. So then I'm going to get, oh, well, that's just 3, right? So, well, you could do it without combining like terms first if you like. And you'll just get 1 plus 2, and the natural log's derivative is 1 over t. So you end up with 3 plus 1 over t. So look at that. It works the same way, either way, with this kind of notation. When you have a dot product or cross product, hopefully will also work. Either way works for that. Okay, so I'm going to erase this to get it out of the way. And let's try it with the cross product before we leave off for today. Alright, last problem we're going to look at today. I think we'll do this one two ways as well. So we'll go the same way about it. First we'll use the product rule, see if it works that way. Then we'll try to check it by just going inside first. So we're going to use the cross product here. Now the cross product can be a little bit intimidating at the beginning, but you'll get really good at it if you practice. So, and it's very, very useful. So that's the other way to multiply vectors. It's the product, where the product becomes another vector. Okay, so we're going to do u cross u prime. But remember, we're going to use the product rule first here. So we're going to say this is equal to the first times the derivative of the second using the cross product times. So derivative of the second is u double prime. And we're going to go plus the second times the derivative of the first, which is u prime again. So I'm going to talk a little bit briefly about what this means. Since this is u prime cross u prime, what vector cross product really means, and we'll focus on learning a little bit more of the physical meaning behind this soon, is if you have two vectors, let's call this like vector A and this like vector B, what the cross product, that multiplication of the two vectors gives you, is it gives you the vector that would come out if you multiplied them and got, like, imagine this going into the screen, so that it is perpendicular to both of these vectors. So it's going to give you another vector out that goes like that. So in this case, you can see that we have one vector times itself. So if you have u prime, if this is u prime, and then u prime is also crossed with itself, there's no angle in between the vectors to use, so it's not like you can possibly get another vector out. So the thing you're going to get out is nothing. So this guy is going to go to 0. You can confirm that with the cross product if you want to, but I'm going to save some time and just use the physical interpretation of cross product here, what it really means, which we're going to work with more. There's just your first little taste, and I'm going to say that that's 0. This is probably not going to be 0, so I'm going to do the good old-fashioned determinant cross product thing. So I'm going to go and say I j, k, and then I'm going to go, the first vector was u, so I'm going to have t squared I'm going to have negative 2t, and I'm going to have 1. And then u double prime, I don't have, but the double prime from up here should be 2 in the x. Derivative of a constant is 0 in the y. And the derivative of 0 is, of course, also 0 because it's also a constant. Okay, so that's the cross product setup. So then you're going to go and eliminate rows kind of like this for the first one, right? So that's the way we're going to do it for the first one. Let me get rid of that though. So that's going to give me I times negative 2t 1 0 0. And then plus, oh, but it's not plus. Remember, it's always going to be minus here because you want to imagine that this is like a determinant from Algebra 2 where you have hiding ones behind there that alternate, plus, minus, plus, etc. So those are called the cofactors, but we'll leave that for another class. You just need to remember for cross product calculations that you're always going to have a minus for this middle thing. So you're going to have minus j, and then if you cross these guys out, you're going to have t squared 1, 2, and 0 left. So t squared 1, 2, and 0, okay, and then plus k, because it's got a plus behind it, and then we cover that row up, so we're going to have this little part left. So we're going to have t squared negative 2t 2 and 0. Okay, and then you just simplify with the determinant calculation. So remember, determinants from Algebra 2 go this entry times this entry minus this entry times this entry. Okay, so we're going to get 0 minus 0 there, really boring, that's 0. So this is minus j, and we're going to have 0 minus 2 there, not quite as boring. And then here we're going to have k and 0 minus a negative, I'm going to write that down, minus a negative 4t. Okay, so that's going to lead to a vector of 0, 2 in the j, and positive 4t in the k direction. So there we go. There's our first way to do this problem. Let's do it another way. So the other way to do it was usually shorter, but maybe it won't be this time. I don't think it is this time. So we're going to take the derivative of after we do u cross u prime. So we've got to do u cross u prime. So I'm going to go I, j, and k. You know what? I need to separate these out a little bit more. So let's go I, j, and k. And u was t squared minus 2t and 1. And u prime was, what, 2t negative 2 and 0. So we're going to go 2t negative 2 and 0. So now we're going to do that cross product. So we're going to have I times, if you think about it, it's going to be negative 2t, 1, negative 2, and 0, minus j, and we're going to have t squared 1, 2t, and 0. Once you're good at this, you really don't even have to write this step down. You'll be doing it so much, but I'm going to do it since we're still warming up. So plus k, and that's going to be t squared minus 2t, 2t, and negative 2. So now we're going to do this cross product. So we're going to have I times, that's going to be 0 minus a negative 2. Then we're going to have minus j times 0 minus 2t. Then we're going to have plus k times negative 2t squared plus 4t squared. Okay, let's see what that turns out to be. So that's going to be 2i, and then we're going to have, looks like plus 2tj, and then we're going to have, let's see, those are like terms, 4t squared, that's going to be 2t squared k. Okay, now remember also we were trying to think about doing the cross product first, and then we've got to go d dt. So now we're going to add a d dt on both sides. So this is going to be d dt of this whole thing. So what's that going to give us? That's going to give us the derivative of a constant is 0. The derivative of 2t is 2, and the derivative of 2t squared is 4t. And you can see that that guy matches that guy. And there you go. So there's another basic vector functions problem. The only new thing in here really was the dot product and the cross product. And like I said, we're going to talk more about those and their physical meanings and all that good stuff as we begin preparing for the AP test. There's one other example in your textbook which you might look at. It's example 3. It talks about finding the intervals on which a vector function is smooth. Basically, let me just write that down. Basically, you know what? I'm not going to write it like this. I'm going to write it in words. So basically, a vector function will be what's called smooth, in other words, no sharp corners or non-differentiable spots, if r prime, if r prime of t is not equal to 0. So not equal is not equal to 0. Because if the derivative of the vector function is 0, remember this is a vector function now and we're thinking about things in kind of a parametric sense. If the derivative is 0, that means that's like a critical point. And since it's a vector function, I mean, if it's a vector function and it's parametric equations, it's not like it's going to be a maximum or minimum. That would be a place where it's actually smooth. It's going to be the other kind of situation where we worried about critical points, like coming from the bottom, those places that potentially produce sharp corners and cusps and so forth. So if a vector function's derivative is 0, then that's basically going to be a sharp corner or a cusp, most likely, and hence it won't be smooth at that point. It could also be, it could also be potentially something like an asymptote, but of course that would also not be smooth, if you will. All right, so I will see you next time.